Let's see. Today we're going to we finished, this is an amazing thing. We are actually on schedule. I don't know if you looked at the listing of the lectures. And, okay, how many people have been reading the notes? Wow. Okay, everybody, at this point, even if it's not true, put up your hand high, because you wouldn't want to admit it to me, because you need to read the notes, okay? It's very important. Okay, good. Have you found, I don't know, I'm asking you to read the notes, so anyway, if you find errors, please pass them, or if there's things that you don't find clear. Is there any questions or feedback that people have about reading the notes? And also, you have to really read the notes before you do the homework, okay? I know it's tempting to just say, oh, I'll just do the homework, okay? But it's really not the right way to go at it. Read the notes first, and make sure you get your head around the material, and then do the homework, okay? So are there any questions, or? We're pretty much on schedule, amazingly enough. I know there were a couple of homework problems I thought I briefly, maybe there's like at least one homework problem I thought I briefly discussed, okay? It's my personal favorite homework problem. It might not be yours, but let's see. So the document camera. Should go over now. Oh, I forgot my microphone. Oh, shoot. Okay, the audio quality's not going to be as good. Maybe I'll just speak louder, okay? So there was a problem, I was here early too, but it just slipped my mind. I like this problem here. How many people did problem 7? You're supposed to do problem 7, right? Wasn't that 7 supposed to be done? Did anybody do problem 7? Did anybody try problem 7? Yeah.
Very difficult.
It's very difficult?
Yeah. I don't know.
Okay, so everybody knows what a DFT is, right? Okay. And everybody believes that circular convolution, okay, is, in fact, it shouldn't be that difficult. Basically, show that the DFT is an orthonormal transform by showing that the columns of the matrix are orthogonal and normal. So formally, this means that this is true. Okay, so, can you do this? That's pretty simple, right? There's a little trick to this. If you're an electrical engineer, at least if you went to Purdue, or if you took like undergraduate civil systems with me, okay, you'll know how to do this, okay? But there's a little trick, which is that everybody knows this, right? That the sum from like n equals 0 to n minus 1 of a to the n is equal to 1 minus a to the n over 1 minus a, right? Is that correct? Yeah, that is less than 1? Yes, if a is less than 1. Less than, and this is an interesting part, less than or equal to 1, okay? So it actually works in the equality case. So if you have like the sum from n equals 0 to n minus 1 of e to the j 2 pi k n over n, right? This becomes 1 minus e to the j 2 pi, and this becomes k times n over n, right? Over 1 minus e to the j 2 pi k over n, right? So the n's here cancel, right? And this whole thing is 1. So this whole thing here is 0. So that sum is 0. Except, so this is if k is not equal to 0. But if k equals 0, then this is just 1, okay? So it's just n, okay? So that sum there is n times delta of k, but that's not actually quite true, because actually this is true if k is any multiple of n, because it's a periodic function. So it's actually equal to n times the sum from, say, m equals minus infinity to infinity of delta of k minus m times n. It's, in other words, it's a, ooh, why is that? I have a shadow there. Anybody know why there's like a shadow there?
Smudge on the camera?
Oh, maybe I touched this with my pen or something. Oh, there is. You're geniuses. Ah. Who says that engineering is useless? Okay, anyway, so, right, so what happens is that this relationship is absolutely fundamental, because it means that these things, what it really means is, if you have, like, f of, so, okay, let's say I have, like, t, okay, is, my notation may be different here than in the problem, because I'm kind of winging it a bit. But this is like E1 through En, or E0 minus En minus 1, right? Okay, so these are columns of the matrix, and if, like, Ek is going to be e to the j 2 pi k n over n, like this, right? Where this is a vector now, right? So index n goes down this way. Then what it really means is that, so each of these is the basis of the DFT. Right? And if I take these guys and divide by 1 over the square root of n, right, in the definition, then what happens is that the inner product between Ek and, say, Em, this is going to be delta of k minus m. Right? So, so it's 1 when the k and m are equal, and it's 0 otherwise. So this means that they're orthonormal, right? Because they're orthogonal and they're normal, right? Now, so that's just what this is here. So these are orthonormal. So this is easy to show, right? It says here for m and n and k less than n and greater than 0. So does everybody know how? I just did this for you anyway. Does everybody know how to show this then? Okay. Now, show that the inverse is given by that. Well, that's like, that's easy. I mean, well, okay. It's almost like the application of the definition. But, I mean, everybody should know that. How many people here have taken linear algebra? Okay, good. So, orthonormal matrices, the inverse of an orthonormal matrix is transpose. So, for those of you who haven't taken linear algebra, what happens is this. So, actually, people tend to think, so you have a matrix, right? A, okay? And then you can have its transpose, A transpose. Everybody knows what the difference is between A and transpose, right? You just, so this is like A, right? And then in A transpose, you flip the rows and the columns, right? You swap them like that, right? Now, there's a tendency to feel like that at the inverse, the transpose of the matrix is its inverse. Because you're sort of reversing the flow of the operations if you think about it. So, but just because you reverse the flow of something doesn't mean you've inverted it. So, for example, I don't know how many people know about projection in homography and back projection. We do that in 637, but not everybody's taking 637. But the forward projection and the back projection are adjoint operators or transposes. But they're not inverses. You have to do filtered back projection to get an inverse. Okay? So electrical engineers tend to have the deeply held belief, deep in their soul, that all transforms are orthonormal. So they believe that the transpose of any operation is its inverse. But that's a false statement. Okay? So for instance, okay, so examples would be, another example is, so back projection. That's one operation. Another one is match filtering. How many people here know what a match filter is? So that's, you know, when you have an impulse response of a system is the time reverse of the signal you're looking for, and that's called the match filter. So that is exactly the adjoint operator. But it's not the inverse. In fact, there was a person, last time I took this class, who does work in SAR, and he really found that to be an interesting thought, because if you live in the world of SAR, synthetic aperture radar, that there's like a deeply held belief in their souls that the match filter is the optimal solution that they strive for, okay? Except for that deeply held belief is false, okay? Because it's not optimal, because it's not the inverse. It's just that, well, there's a long history. It turns out that it's optimal in some context. You have white noise, gives you the maximum noise ratio at a single point or whatever, but you can do much better than a match filter. So the adjoint is not the inverse, except when the transform is orthonormal. When the transform is orthonormal, then the adjoint and the inverse are identical, okay? And that's really easy to show, and you should be able to show that, okay? It's basically just a matter of plugging into the formulas, okay? So I'm sort of, okay. So now, okay, now show that it's a diagonal that this thing, if I take A, okay, so A here is a circular matrix, okay? So it's a diagonal matrix with entries given by the DFT of H, okay? Well, it's a circular matrix, okay? So if you just look at it, this is really, step C is really easy. This is not a hard problem. You just have to actually just follow it and not panic and do one problem at a time. Because if you just plug into this, you're going to just get the DFT. I mean, this looks complicated, okay? But the actual application, if you multiply A by T inverse, okay, which is now the transpose, you know, you just actually get the DFT. It's just an explicit formula for the DFT. And then, hold on a second. Yeah, so you've taken, I mean, you just do it. It falls right out, okay? So now you've basically shown that the eigenvalues of A have to be this lambda, because you've shown that the T diagonalizes the circular matrix. Now it gets a little more complicated. Shows that the logarithm of the absolute value of the determinant of the matrix is given by this. Okay? Well, I mean, that's actually pretty trivial, because you know that the determinant has got to be the product of the eigenvalues, and now you have an explicit form for the eigenvalues. So this just seems like you panicked long before you had any problem with this problem, okay? Did you do this problem, by the way? If you did, okay. Did anybody do it? Well, this was the sign? Okay, I'm not picking on I just learned. This was the sign, right? Okay. Nobody completed the assigned homework, okay? I'm going to put these problems on the exam, and then you're going to have a bad day, okay? And I tell jokes now, but it's not going to seem funny when you get the exam back, okay? Okay, now, I can be a mean person, okay? Ask the Purdue administration. Okay, now what happens is you take this thing here, okay? I know what you do is you just say, okay, well this is you divide this by n, you take the limit, and this is looking like a sum, okay? Okay, now, this is the part that might be a little confusing. The lambdas are the DFTs. This is actually, part F is the only hard part, okay? And it's actually not that hard. The lambdas are the FFTs of the original function. The H is a circular matrix which has entries of H. It's a circular matrix, okay? So this function H, the eigenvalues are going to be the DFT of H, okay? Okay, so everybody wake up for just a moment, okay, and give me the next 10 seconds of your attention, okay? This is a matrix A, okay? It's circular. And I'm telling you that you can diagonalize a circular matrix with the DFT. And the eigenvalues, the entries that are diagonal matrix, are the DFT of H, okay? So what happens if you have a function, and you have a function, right? I'm drawing this as a continuous function, but let's say it's really discrete. It's too much trust. And I have a window. I window it to some window, and I take the DFT, right? If I keep making the window bigger and bigger and bigger, eventually I get the what? Now, the people who are not signal processors may not know this, but yeah. You get it's called the discrete time Fourier transform, okay? You get the discrete time Fourier transform, okay? The only thing that's an issue here is you have to figure out where 0 is, okay? I mean, there's some little technical details in the definition, because the DFT is defined as xn times e to the j 2 pi kn over n, where you sum from n equals 0 to n minus 1, right? That's the so-called the endpoint DFT, okay? The formula for the discrete time Fourier transform is almost the same. It's just that you take the sum from n equals minus infinity to infinity of xn times e to the j, and this is going to be 2 pi kn, right? Or you just make this whole thing omega. Usually is the way to do it. Okay. So, basically, you just fiddle around, and the DFT coefficients are, this thing here is the discrete time Fourier transform. The discrete time Fourier transform is the Fourier transform of the discrete time signal, okay? It's just the way you take the Fourier transform of the discrete time signal. You can't take the continuous time Fourier transform of the discrete time signal. So you have to do something. This is what you do, okay? And then you have a thing called the DFT. The DFT is what you can actually do on a computer. You can't do the discrete time Fourier transform on a computer. Why? Because a computer doesn't have an infinite amount of memory. To do a DFT, you have an infinite number of input samples, and the output is a continuous variable, omega. So this is x of omega. Right? You can never really compute the Fourier transform of the discrete time signal on a computer unless you did it like in analytical form or something. Okay? What you do is you compute the DFT, and it's an approximation to the DTFT as the window gets large. Okay? So basically, over here, that's why this is a good problem to do. You really should do it. I know you're not going to do it, okay? But you should do it, okay? Hold on, where did I just do it? Keep doing it. What did I do with my notes? Oh, here it is. This is a great problem, though, because it causes you to go through all these different steps. You really have to use all these ideas, and every step is really pretty simple, okay? So these lambdas are just samples of the Fourier transform of H. So you're basically looking at samples that get closer and closer. It becomes an integral. H of omega here is the Fourier transform of the discrete time signal. So this is important because it tells you something that's really fundamental about the determinant of circular matrices, which, I don't know, the last few times I was at cocktail parties, and you're having conversations, and then someone said, You know, I really don't understand this thing about, like, computing the determinants of circulant matrices asymptotically as n goes infinity. And I was like, oh, well, you know, so you really need to know this if you're going to have, like, social interactions. It's going to be, you'll impress your friends, you'll get better dates. You know, it's really the thing you've got to be doing. Okay?
What if she's not an engineer?
Huh?
If she's not an engineer, this would be like boring.
No, because then, you know, well, it worked for me. What can I tell you? Okay? Okay. All right. I got you. At least you woke up. Okay. Here you go. Okay. All right. Do the problem. Okay. Good. Now. Next, non-causal model. Are there any more questions? So there's also two other tricky problems. There's one other tricky problem where we have to figure out the autocorrelation. Hold on. Analytically, power spec. Oh, you need to calculate the autocovariance in X. That's a little tricky. Did you get? How many people tried this one and got it? You should be having questions, by the way, in class. If you haven't gotten the homework a problem, then you're clearly having a problem. Okay, so I should know about it. Let me know. I mean, okay. I don't know if I mentioned this before. Okay, but now that some of you are actually reading this, I want to point out something, which is the exams are going to have these problems on them, okay? Let me repeat that one more time, okay? The exams are going to have these problems on them, okay? So you need to know how to solve them. Go and solve them. You're allowed to talk to each other, okay? I don't care how you get the answer. You can look it up on Google, okay? But you have to write it down yourself, because in the end, you're going to have to do it on the exam. The exam will be closed book, notes, and everything, okay? So you're going to have to really know it. So you either have to memorize the solution to every problem in detail, okay, which there's a few people out there probably could do that, okay? It's sort of like the application of genius to evil or something. Or you're going to have to actually understand what you're doing, okay? So don't come to me crying later, okay? Go study it, okay? Work the problem. Even if you can't do everything exactly right, okay, you should at least come back with questions. This one's tricky. How many people got this one?
I'm staring at some people.
Huh?
I haven't started the homework.
You haven't? Okay. It was due already, right? Just check it. I'm picking on him because he seems like a nice guy. So, okay, come on. You're going to have to go do that. Or, you know what? It's easy to just have me stand up here and talk to myself, okay? Okay, now we're going to talk about non-causal. So the problem is, okay, so why not causal? Causal is okay, but the problem is that, okay, in 1D, causal is okay because we take the past, okay, we predict the present, okay, and from that we were able to build a model. Basically what you do is you multiply together the probability of every new observation given the past observation, okay? And you can actually represent, we only did the Gaussian case, but this is quite general. You could really look at, I mean, just a little more generally, let's say you have this, you know, you have a sequence, so you can take xn, okay, you can take the probability of xn, right, times x, and I'll put here less than n, so you're taking all the things before time n, okay, and then you can multiply that by the probability of xn minus 1 times all the things before n minus 1, right? And you can just continue that. Okay? So, this whole thing then is the probability of the entire sequence. So we can, prediction can be used to model the distribution of things, okay? And it's really quite general. So what's the problem? Well, the problem is a few things. It actually turns out in 1D, causal models like this are completely general, okay? But in 2D, you have problems. First of all, in 2D, you go to something like this. Okay, and you use, let's say I use these pixels to predict this, okay? So the problem is that, okay, so that's all fine and all good, but what's going to happen is that if I make a model like that, there's going to be an orientation to it. So the spectrum of things that I produce, like for instance, you can actually have specific examples where the power spectrum or the autocorrelation function of this random process in the Gaussian case has symmetry, but generally speaking, it won't be symmetric, okay? The family of distributions parameterized this is not symmetric, which is to say that if you have one model with one sort of distribution of autocorrelation function, and you say you transpose it by flipping the rows into columns, then that model won't be in the family in general. Yeah?
So if you go back to the causal model, you're trying to predict the present from the past.
Right.
Now, can you predict the present from the future and it's perfectly symmetrical always?
Yeah, so you could reverse this whole process. Okay, we haven't even gotten there yet, but later in the course, at some point, in fact, okay, here's a proof. In fact, what you're saying is exactly true. Maybe, I forget if it's in the notes or not, but I don't think it's in this section of the notes, okay? First of all, there's all kinds of cool things that are true, okay? Okay. If this is a Gaussian random process, okay, then I know, I proved to you in an earlier lecture, that and I think it was stated in the notes, okay, that any Gaussian random process is reversible. Okay, what does that mean? So if I have it, okay, first of all, to be a reversible, okay, that statement was false. Okay, this is why I have to write these things down in order to be true. Because like what I say verbally, there's technical errors I make. Okay, but for any stationary Gaussian random process, okay, is reversible. Because if it's a stationary Gaussian random process, then it's completely characterized by its autocorrelation function, right? And its autocorrelation function is a symmetric function of time. So if I took the random process and reversed it, I just flipped the index, the reverse process has the same autocorrelation. So its distribution is the same. If its distribution is the same, then if it was a pth order AR model, it's still a pth order AR model. So in other words, so the optimal predictor in the causal direction is also the optimal predictor in the anti-causal direction. That's an interesting result. I've proved that all without writing anything on the piece of paper, just by going through a sequence of logical implications, and that's a rigorous proof.
So you're trying to draw a distinction here with these 2D models, saying that it's because you have to impose some ordering, your filter might be symmetric, and then this causes a problem.
Right.
Right. But there's an ordering in the 1D model, right?
Yes. so there's ordering in the 1D model, but the interesting, or perhaps disturbing result is that we're going to talk about non-causal 1D models next. And I'd like to tell you that they're really powerful, okay? And maybe they're of some value, but their value is actually limited, because in fact, they're no more powerful, okay? They are no more expressive than the 1D causal. In 1D, non-causal models are no more expressive than causal models. Okay, and we're going to actually make that formal later in the class and generalize it to even non-Gaussian processes. So it's sort of a counterintuitive thing. So I'm going to give you a preview of the future. And if you use the last, say here, P equals 3, I use the last 3 samples to predict this sample, right? Then it's going to turn out that I could use the last 3 samples and the next 3 samples together to produce the current sample, okay? And if I model it non-causally, I'm jumping ahead here, because I haven't even said what it is to model something non-causally yet. Did you read the notes? Okay, good. You see, that's the advantage. So you know that we're going to develop a non-causal model, but the non-causal model is no more expressive than the causal model. Actually, for the Gaussian case and for the non-Gaussian case in 1D. Yeah.
Okay, so I'm going to draw an analogy. See if it's that way. So you know how they say that it's proof that the rational is countable?
Yeah.
Because it's a two-dimensional space, the rational numbers, and then you just have a pattern for ordering them in one dimension, and then you map that one dimension onto the natural numbers, and then you've got to prove that the rational is accountable infinite.
Yeah, that's true.
Right? Okay, so you've got a two-dimensional grid, and you can always come up with a one-dimensional ordering for a two-dimensional grid unless it's something like the real numbers.
Yeah.
But we're not talking about cases like that. We're talking about cases which are discrete.
Okay, yes. Okay, that's a very good point. And by the way, it's an excellent question. And I'm going to address all this in detail, like way later in the course. Okay? Okay? In fact, but it's really good you're asking it now. And it'll help you to pay attention between now and then, okay? Okay, but because we'll like formally state all these things, okay? You're absolutely right, because if I order these points like this, right? And if I make that point, if this is a 2D stationary random process, and I make a conditional distribution of that point dependent upon all the previous points, right? Then that is completely expressive, okay? So all models are included in that case, okay? So you're saying if this is completely expressive in 1D, because I can map the 1D line to the 2D plane, then this is completely expressive. That's true. But if the order is finite, it's not true. So what happens is this. Your question is so good I can't help but answer it, okay? This is why, by the way, guys, okay, the two messages of this class are what? One, you must read the notes, right? Okay? And two, you must do the homework, okay? To the best of your ability. But definitely read the notes, okay? And the reason is that you're asking a very good question, and if you haven't read the notes, you won't know what I'm talking about right now, okay? Okay, so if you just make this point here dependent upon the 4 surrounding points, okay? Okay? And then you say, okay, so that's a model, and we're going to make that formal. That's a Gaussian Markov random field, say, with just a 4-point neighborhood, okay? Then the question is, if you take that same random field and say, let it be of infinite size so that we don't worry about boundaries, and you ask, how many points do I need to have in the neighborhood in order to be able to predict this guy here? Okay? So how big does this neighborhood have to be? And the answer is, the neighborhood has to be infinite, okay? So you've taken a model of order 2, okay? Because actually it turns out there's a symmetry condition. And if it's a stationary random field, then that prediction coefficient and that prediction coefficient has to equal that and that. Okay? These two have to equal and those two have to equal. So there's only 3 degrees of freedom to this model because you have 2 prediction coefficients and 1 prediction variance. Okay? So you've taken a model with 3 parameters, okay, and you've replaced it with a model with an infinite number of parameters. And parameterization is the name of the game. Okay? You don't just want a model that fits. You want a model that fits parsimoniously, okay? That fits economically. You want the least expensive solution of the highest quality, where cost is in terms of parameters. Parameters are the coin of the realm, okay? Because parameters, we'll see later that there's a fundamental issue. The parameter estimation, the more parameters you have, the more data you need to learn those parameters. Okay. So the fewer parameters you have, the better. That's where this whole concept, if you've been reading in literature, there's a lot of talk about sparsity these days. Okay? Sparsity is all about minimizing the number of parameters in your model. So this is a really bad trade-off. Okay? Yeah.
Just have a follow-up question, very much related to that. So by ordering pixels of an image in 1D fashion, can we? Is there a particular order such that we can get rid of non-causality for a particular model?
No. And that's, well, I mean, that's an informal statement, okay, but there's no formal restatement of it that I know of which is true, okay? So, what happens is that, so that's why I was saying that you can find coefficients in a model that does have a neighborhood here, okay, and this is actually from the last section. So there's a figure in here. There's this figure here, okay? So I call this a p-order model because we have p earlier rows we use and p earlier columns, okay? And so p equals 2 here, okay? So if you have generally a model with this window, okay, and it'll have some spatial autocorrelation, and if you took that autocorrelation and you flipped it like this way, okay? Oh, by the way, in 2D, okay, so autocorrelations are symmetric along one axis, but not along both. So if you have an autocorrelation function, so this is another common misconception. People think that, so in 2D, if you have a random process and say that's just autocorrelation, it looks like that, right? So if I take the x-axis and just flip that, if I time reverse just one axis, then yeah, I will get something different, because then I'll get something that looks like this, so if you have like a correlation, if the autocorrelation is oriented along the axis corresponding to x and y together, right? Then if I reverse time in x, then it will definitely be different, okay? So in 1D, yes, the autocorrelation is symmetric, but in 2D, it's symmetric, but it's symmetric in both variables, not just one. So if I have R as the autocorrelation of C3, and I have MN, that's equal to R of minus M minus N. But it's not equal in general to R of M minus N. That's not true, okay? So, in general, if I take some random process generated with this model and I flip it along one axis, it won't have this form anymore. In fact, it will have the form where I would have had to have flipped the prediction coefficient, okay? But that's not a valid one. So you say, well, I could do that one too. But there's something satisfying about this, right?
We may need to add more constraint that would make the model non-generic.
Yes.
Then we might be able to do that.
Right. You could add more constraints that would constrain it, but then the expressiveness of the model would be limited a lot. Okay. So yeah. So you've got to read this section here, and by the way, the general concept of toplet matrices turn to block toplet matrices. Okay? The way ends up happening is in 2D, if you have a toplet autocorrelation, if you have a toplet matrix which corresponds to a space invariant autocorrelation, right? Then what happens is that you take you read this, guys, right? So what happens is that you raster order the images, the typical thing you do. So you take individual rows and you make one long column vector out of the image by breaking it up into pieces, and each piece corresponds to a row of the image. So then what ends up happening is autocorrelations or filters have block structure. So they become, so this H matrix here from equation, where was it defined? In section 3.4, it's in figure 3.4, this H matrix breaks up into blocks. The blocks have a toplet structure, and each block is toplet. That's because this is space invariant along the row and the column direction. So the blocks represent well, it depends on how you view it, but they represent the rows, or they represent the columns, I guess. It depends on how you use the word. But one represents the rows and the other one represents the columns. Okay? You've got to sit in and read this carefully and get your head around it, okay? Why? We'll review this. Because if you come to lecture and you haven't read the notes, then you won't be able to follow what I'm saying. And if you haven't done the homework, you can't do the exam. Okay? This is this balance of terror thing. Okay, anyway. Good. Okay, so now, I didn't forget what the question was anymore. Did I answer your question along the way? Yeah, okay, good. Okay, good. So that's motivates the need for non-causal models, because in 2D they're going to be a lot more expressive and more general. Okay. Now, so now what happens is, instead of having a causal prediction, we have a non-causal prediction. So each pixel is predicted by a combination of the pixels after it and before it. Okay, and then we have, into the Gaussian random process, we have the conditional expectation of xn given all xi for I not equal to n. Okay, and then so then the prediction error becomes this thing. So now what happens is that you have this matrix G, right? So okay, one thing that's very important here is that okay, and I'm not going to prove this, but this is a general result. So whenever you have a minimum mean square error predictor of something given something else, okay, then the prediction errors are going to be independent of the things that you use to predict them. And it's intuitive, because if there was information left, if there was correlation between them, then you could use that information to do a better job of predicting. Okay? It's sometimes referred to as the orthogonality condition. Okay, now, so what happens is you're going to have basically G. So G here, you have X. G times X is going to be the prediction value, right? So the prediction errors is going to be X minus G of X, right? So that's going to be just the identity minus G times X. This is just like what we had before, but now this sucker is no longer lower triangular. So what ends up happening, it has zeros on the diagonal, because you can't use your current values. And it's going to have entries in both sides here. Oh, I should make those look like zeros. I'll make them squigglies or something, okay? Because they're G, okay? Now, you might think that G is symmetric, and when the random process X is stationary, it is. But in general, it's not, okay? It's not necessarily symmetric. Okay, so now we can look at the density function for the distribution, because that's ultimately what we want. To me, in this class, a model means a distribution, okay? A probability distribution. So So the density function of any Gaussian random variable is going to be this. Now B here is not the covariance, it's the inverse covariance. And that's often called the precision matrix. You know, the covariance matrix comes up because if you're trying to estimate, covariance is a natural thing to estimate, right? You just take the product of things and you multiply them together and average, okay? But it turns out the inverse of the covariance is often the thing that's more, gives you a lot more insight into the problem. And it's inverse, in one-dimensional case, it's inversely related to the variance. So as the variance of something decreases, its precision increases, right? So the inverse of the variance is the precision, so we call this the precision matrix, okay? Now, so now what happens is that, okay, so now we're going to play some tricks, some mathematical tricks, and you got to read this because it's like super obvious once you see it, but it's not so obvious before you see it, okay? So, so you have some distribution here, and you know, you want to calculate the conditional distribution of one value in X given all the other ones, and you know it just has to have this general form. There's got to be some linear predictor that's optimal, and there's got to be some prediction variance, and this is just a normalizing constant. You just don't know what these values are. So now you have like the question, well, you can relate this form to this form and say, you know, what are the values of G that will equate with the values of B? So from B, I should be able to calculate the G's, and from G's, you would think I should be able to calculate the B's, okay? So what do? I start taking logs and I differentiate, and I'll let you go through that. You can just do the calculations, okay, and you start differentiating, and you get this expression here, okay? You get this expression, and then you start equating things, and it's pretty clear, I'm going to let you go through this, that Bij is got to be equal to this, okay? So, what does all this mean? The diagonal elements of B are going to be the inverse variance of the prediction, non-causal prediction error. That's a long sentence. I'll say that one more time. The diagonal elements of B, if you take a diagonal element of B, it's the inverse prediction variance for that point, okay? But it's got to be the non-causal prediction. And and then all diagonal elements of B are basically proportional to the prediction coefficient. So, it's kind of an amazing thing, and this is the formal structure of the thing, okay? Now, one thing, I forgot to tell you, is, maybe I prove it later, is that, that comes in the next section. Now, something that's really interesting, so are the prediction errors, when non-causal prediction errors, are they independent? No! They're not independent. Gee, that's kind of surprising. So when you take the prediction errors are not independent. Where is this? Okay. So it turns out the power spectrum, this is 4.7. This is the power spectrum of the prediction errors. They're not independent. It's not white. If they were independent, then the prediction errors would be uncorrelated and it would be white noise, and the power spectrum of the prediction errors would be a constant. But this has a spectrum. Because you know why? Because you're cheating. You're using the future. When you use the future, it correlates to prediction errors. So, you're running down there predicting each of these guys, and as you predict each guy, they're correlated. Maybe not, you asked me a question last time about somebody asked me a question about why they felt that the prediction errors should be correlated in the causal case. And I said, no, that's a false argument. But that argument probably was correct in this case, okay? Because here you do have the interdependencies that make them correlated. So your intuition that the prediction errors are uncorrelated now becomes wrong, okay? So you have to be really careful about that. And let's see. Okay, so we're basically out of time. Let's see. Prediction errors. So you're going to read the notes, right? Hold on. Stop camera. Okay. Is this it? Okay. So we're almost out of time, but you're going to read the notes. At this point, it becomes really important because this stuff is new, okay? and I don't think it's like so bad. So read the notes, okay, and do the homework. Bye. Okay, so read the notes.